fact that the magnitude of the amplitude is given by the expression which is equal to square root of x square plus y square, and the intensity therefore can be expressed as a multiplication of the real and the complex conjugate parts of A star giving us the modulus of A square, with A defined as A x plus I y and A star defined as x minus A y. This is now telling us that we can get to the intensities from any scattering. So, this is representing one single wave, but we can have multiple waves. The phase that is associated with it, tan phi, is equal to y divided by x. Now, if there are a large number of such amplitudes, because that is what happens in a crystal, then the overall amplitude which comes out, the so called resultant amplitude, is sum over individual amplitudes. So, the resultant amplitude is sum over individual amplitudes, and that is given over the sum over 1 to n of modulus of A n exponential I phi n. So, you see that this resultant is the representation of f of h k l. So, therefore, you see that it is sum over 1 to n, we can write it as a real part plus I times the imaginary part which is associated with I. So, the real part and the imaginary part together will define our resultant A. So, now you can imagine a situation, or you can create a situation where you write here the overall structure factor capital F, and then this will be f of HKL, individual HKLs going from 1 to n, the total number of reflections. This also could be an individual HKL value, f of HKL, f of HKL. This is f of R, f of overall resultant, capital F. So, for an atom at xyz, the amplitude is f and the phase change is 2 pi, which we have calculated in the previous classes to be 2 pi hx plus ky plus Lz. This we worked out with the fact that it can be done for any plane HKL and any position of the atom x and y and z n. So, if there is an atom at xyz, the amplitude of course is always f depending upon the content of the electron density at that position vector xyz. So, if there is a carbon atom, there will be 6 electrons, nitrogen atom 7 and so on. So, we can therefore write the expression for the structure factor. Remember, until now we were discussing the intensities because that is what we measured, and now we are writing the expression for the structure factor. So, the structure factor is 1 to n f of n exponential 2 pi I hx plus ky plus Lz. So, what you therefore see is that now the phase factor can also include the imaginary component. In the case of a centrosymmetric structure, this imaginary component will not be there, it will become a cosine function only. But in case of the general crystal structures where we have non-centrosymmetric materials also, this will be the expression. So, this is another key expression for our calculations in the future. So, this is the expression for the structure factor. You see that there is no modulus written here. So, it is actual structure factor, modulus and the phase together, and this is the expression we need to dump it into the Fourier transform expression of rho of r, so that we can get to the rho of r. So, this is the value which we need to compute electron density. So, this structure factor therefore can be also written conveniently in this form, cosine plus I sine. For the centrosymmetric system, as I mentioned again and again, only this term will be there, and this term now will be 2 times that, because this will vanish and this will be now there 2 times over n by 2, but it is equal to 1 over 1 to n f n cosine 2 pi hx plus ky plus Lz. How does that come about? We will see as we go along. We will see this right away. So, for the centrosymmetric structure, atoms are at xn, yn, zn, and minus xn, minus yn, minus zn. So, that is the definition. That means we are taking the origin as 0 0 0 as coincident with the inversion center for the any crystal structure which is centrosymmetric. So, there are so many centrosymmetric space group as we have already learnt, and all these space groups will have this property of having xn, yn, zn, minus xn, minus yn, minus zn, apart from other equivalent positions which will come due to the operation of symmetry elements. So, if it is P1 bar, these are the only 2 positions, but if you go to higher systems like P21 by C and so on, you will get other equivalent positions, but the common factor is that we have the xn, yn, zn and minus xn, minus yn, minus zn, which therefore defines our center of symmetry to be at the origin. If the center of symmetry is at the origin, then f of HKL is sum over 1 to n divided by 2, because now we do not have to consider x y z separately and x bar y bar separately, and if we do separate them, then its summation is over only the half the number, because for every x y z there is a minus x minus y minus z present in the crystal lattice or in the unit cell, and therefore this summation is over the unit cell, and this now you see is n divided by 2 fn exponential 2 pi I hx ky lz plus exponential minus of hxn kyn lzn. So, if one evaluates this, the sign terms vanish, as we showed just a few in the previous discussion, and therefore you see that this is equal to 2 times sum over 1 to n by 2 of f of n cosine 2 pi hxn kyn lzn. So, what you do is you consider half the number of atoms, sum them over 2 times and get the cosine function, or the most easy way to program it in terms of programming is f of HKL is equal to 1 to n fn cosine 2 pi hx plus ky plus lz. So, the complete disappearance of the dependence on the imaginary axis is gone. So, there is no complex quantity that is associated with the centrosymmetric structures. So, this value of f of HKL can be plugged into our Fourier transform equation, and we can get the electron density distribution. So, that is where we have arrived. So, we have arrived at a very fairly safer position now. We do an experiment, we do an X-ray experiment, calculate the intensities, and having measured the intensities, having measured the intensities, calculate modulus of f of HKL. So, what is left out is to find out the value of cosine 2 pi hx plus ky plus lzn in case of centrosymmetric systems, and the exponential value, corresponding exponential value in the case of non-centric systems. We also know how to calculate this cosine 2 pi hx plus ky plus lzn with the example we took for cesium chloride. So, it is a fairly straightforward one if you have only 2 atoms in the unit cell, and that is a centrosymmetric unit cell. It was a very easy calculation, but you can imagine that if there are hundreds of atoms, the calculations will be a little more tedious. It is not going to be fairly straightforward. The second issue is the unknowns here are xn, yn and zn. What you have in this information is the information about the modulus of f of HKL, but as long as we do not know xn, yn, zn, we cannot get the phase, and therefore, we have only the magnitude of the scattering that is coming up, and that is why we say it is the structure amplitude. So, the magnitude of f of HKL is called structure amplitude. So, the structure factor is the one which includes the amplitude as well as the phase. So, the amplitude as well as the phase included will be the structure factor, right. So, we go further now. There are lots of equations which will come, but I will go very slowly, systematically of course, hopefully, so that we will follow each other. See, again we come back to the symmetry. That is why we entitled the structure as in the course as structure and symmetry in the solid state, or symmetry and structure in the solid state, in that order, because symmetry grounds the structure and structure grounds the symmetry, and then both of them now coexist handshake in the case of a solid state, and that is why we have given that title rather than saying crystal structure determination or chemical crystallography or whatever, even though the last part of the course will cover mostly chemical crystallography. So, systematic absences is something which we will now introduce. It is a very nice statement, systematic absences, something which is absent systematically. Well, I have an example in my group. There is one person who is systematically absent in all these talks. There are others are attending these talks, but there is one fellow who is systematically absent. In fact, using him I can determine the symmetry in the group, and that as a joke I am telling you this, but essentially systematic absences help in determining the space group of a given crystal system. So, we need to study it in more detail. See, one of the things, I will make a statement now. It is like making a statement and giving a proof, like in mathematics, we give the proof and say QED, right, and similar thing we will do here. The statement that I am going to make is that if in your crystal system the space group involves translation components, watch my words, if in your crystal system the space group involves translational components, whether it is a centering associated with one direction or face centering or body centered. So, in other words, the translation is associated with a lattice, or whether it involves the translational symmetries in the presence of screw axes and or glide planes. And if all these operate simultaneously in the space group, generating our space group, like for example, if you take P21 upon C, in P21 upon C we have the presence of a primitive lattice. So, there is no translational component associated with the primitive lattice. That means primitive lattices will have all the reflections with respect to HKL. So, there are no systematic absences that will come. So, the fact that there are systematic absences coming is a consequence of the presence of translational components in the space group. So, it is not obviously there in the point group. So, it is in the space groups. Luckily for us, crystallization ensures that we have 3-dimensional periodicity. So, the presence of periodicity, the presence of lattice centering will ensure that we will have systematic absence. So, using X-ray diffraction and finding out how the HKL values appear, it is possible to see the translational component associated with the lattice. So, it could be a C centered lattice, it could be an F centered lattice, it could be an I lattice. We will see how it develops. The other aspect is of course the presence of 2-1 screw axis as well as the glide plates. So, let us now take the structure factor expression which we have and see how the structure factor expression reorganizes itself when we have a centering. So, we will start from a C centered lattice. So, in the case of a C centered lattice, what are the extra components you will get? For every x, y, z, you will get a half plus x, half plus y, z. So, if there are 8 equivalent points, you will get 8 other equivalent points associated with the addition of half plus x, half plus y, no addition along the z axis. So, this is the concept of C centering in the lattice. We will take the international tables later on, probably later on during the coming classes. It probably will not happen now, but in the coming classes, so that we now understand the underlying mathematics behind this and the underlying principle behind it, and then we will not have to worry about it once we have this understanding. Then we will go and examine the international tables for crystallography, which we have already seen with respect to equivalent point diagrams and the symmetry diagrams. We have seen the diagram associated where we see only the symmetry that is associated with the space group on the left hand side and the appearance of the equivalent points on the right, and we are now reasonable experts to go from one to the other given the crystal system, point group, symmetry and so on. So, here what we will do is we will get the expertise on understanding how the systematic absences appear. In fact, what international table gives is not the systematic absences, but it gives you this what we could call as systematic presences. So, whatever is present is indicated in the international table. Please remember that. Do not look at the international table and look for systematic absences, because what is given in the international table are the systematic presences. So, you have to look for ones which are not going to follow what is given in the international table before we go to that. So, let us not hurry up and see and go to the international tables right now. What we will see is what happens to the structure factor when there is a C centered lattice that is offering itself in the crystal system. We sent an X-ray beam, we got the diffraction pattern. The diffraction pattern gave us the reciprocal lattice positions as well as the intensities. I measured the intensities. I also got a list of all the HKL values I have. Now, I am going to examine that list of HKL values. What is important for us to remember is that if there is a C centered lattice, the n atoms, just like we discussed the case of center symmetry just now, the atoms there are xn, yn, zn. For every xn, yn, zn, there is a corresponding minus of xn, minus of yn, minus of zn. There are no translation components with that, and therefore, the presence of the center of symmetry or otherwise is not going to be indicated by the so called systematic absences. We will notice that when we look at the international tables and see what are written, what is all written in that systematic absence column. So, if Similarly, here the n atoms are divided into two parts. There is one part which is associated with x, y, z, and the other part which is associated with half plus x, half plus y, z, representing the C centering in the lattice. So, what is the effect of that on the structure factor? One is, of course, each of them has half of n. So, if n is the total number of equivalent points, m is half of n. So, I hope these equations are fairly clearly seen in the projection. You see it all right? Okay. So, f of HKL therefore can be written as sum over 1 to n. This is our general expression which we just now derived, Fn exponential 2 pi I for any crystal system, be it centrosymmetric or non-centrosymmetric. For any crystal system, sum over 1 to n is f of n exponential 2 pi I hx plus ky plus lz. We now know this is the factor which is the phase factor, and this is the corresponding amplitude coming due to f of n, and we know also that f of n falls with sin theta by lambda. So, it depends upon the scattering angle theta. As theta increases, the value of f n keeps on decreasing. We know that and we have understood it thoroughly. So, now what we will do is, because of the fact that there is C centering, we factorize this into two components. So, we have sum over 1 to m. The first part corresponds to x n, y n, z n. So, this is exponential 2 pi I h x n plus k y n plus l z n. The second part corresponds to x plus half, y plus half and z. So, we separate these two. So, this is sum over m now, but there are two components, one corresponding to half of n, the other corresponding to the other half of n. So, we have therefore this expression exponential 2 pi I h x n plus half, k y n plus half plus l z n. I hope the speed with which I am going is okay. So, you are all with me. So, this is important, particularly when you are looking at the video and trying to get the hang of it. If I hope I am trying to adjust to the speed with which one can interact, because in a classroom you can sit in front of me and I can see your heads nodding, but when in a case where you are observing it on a video, I do not know whether your head is nodding or whether you are sleeping, right. So, I will adjust the speed in such a way. I hope that you will be with me all the time, and please follow this indicator which is nicely red in color. So, I will be following that with the equations. So, let me repeat this part to keep your concentration intact. So, when we go to the general expression of f of HKL, this is the general expression for HKL. So, it is 1 to n, n is the total number of atoms in the unit cell. Now, this n is becoming half of n in a C centered lattice, and therefore, I have now the summation over 1 to m is equal to n by 2, and then I write the expression which is associated with x n, y n, z n, and this is the expression which is associated with x n plus half, y n plus half and z n. So, there are n atoms associated with the entire system, half of it with respect to this and half with respect to that, and that defines a C centered lattice. See, this is the advantage of symmetry, this is the advantage of crystallization in a C centered lattice. Effectively what it means is that if once you have this 1 to m measured, that means the number of atoms which you are looking for is now halved, because we have to determine only the m positions, because the other half is generated by this. That is advantage number 1. The advantage number 2 is something will happen to these FFHKLs. What will happen to these FFHKLs is what we see in the next part. What will happen is I can rewrite this expression as 1 to m f of n exponential 2 pi I hx plus ky plus lz. So, what I do is I take the common factor out of this. So, once I have this common expression fn 2 pi I to exponential 2 pi I hx plus ky plus lz, then this will be multiplied by this, now becomes value equals 1. So, because we have this taken out, so it is 1 plus exponential 2 pi I. Now, what is left in this expression is h plus k by 2. So, this is the additional half values associated with h and k. So, this is exponential 2 pi I h plus k by 2. Notice that h and k are integers, and therefore, this is a mathematical quantity which can be evaluated. Exponential 2 pi I h plus k by 2 we can evaluate mathematically, and that is given here. We can expand this as cosine pi h plus k plus I sin h pi h plus k. So, this exponential factor with the integers can be calculated straight away, and it so happens that this has a value minus 1 to the power of h plus k. So, if you evaluate this expression mathematically, we get this as minus 1 to the power of h plus k. So, this minus 1 to the power of h plus k can replace now this quantity. So, we will have this as 1 plus minus 1 to the power of h plus k. So, the value of h and k therefore, will get restricted by this condition. How they get restricted by this condition is shown here. Since h and k are integers, f of HKL is equal to, this is clear? Okay. F of HKL is equal to 1 to m fn exponential 2 pi I hx plus ky plus lz times 1 plus minus 1 to the power of h plus k. So, now the value that comes up for a HKL reflection depends upon whether this value minus 1 to the power of h plus k is evaluated the way it has to be. So, we substitute different values of h and k. So, if h plus k, this quantity h plus k is even, that means if suppose you have a reflection like in the k, let us take an example, suppose we have a reflection in the diffraction experiment which is 1 1 0. So, it is h equals 1, k is equal to 1. So, h plus k is what? H plus k is 2. That means it is even 2 times n is equal to 1 here. So, h plus k is 2. So, when it is that value, then this minus 1 to the power of h plus k will just give an additional 1 to this quantity, and therefore, you will have f of HKL as equal to 2 times this value, that will be 1 plus 1. So, it will be 2 times sum over 1 to m fn exponential 2 pi I hx plus ky plus lz. So, you notice that this is now 2 times and we are summing it over only the half the number of total number of atoms in the unit cell. So, the effort is reduced to 50% and only for the even values of HKL. L is not is immaterial in this calculation because it is a C centered lattice. So, in the C centered lattice therefore, we have h plus k is equal to 2n plus 2n, and whenever it is odd, let us say we take a reflection 1 2 0. In case of a reflection 1 2 0, 1 plus 2 is odd. So, the value of f of HKL is 0. That means there is no structure factor value, that means there is no intensity. So, that is why we call this as systematic absence. So, all those reflections in among the HKL, all the general reflections, we call them as general reflections. HKL reflections which are measured in the entire experiment, if you measure them, you will see that all those values for which h plus k is odd will not be there. So, if you just now display your reciprocal lattice in such a way in which you look at the way in which the reflections appear, all the h plus k odd values will not be there at all. That means you do not see any reflection that is coming out from the experiment. So, experiment generally now dominates of half the set of reflections, and they come twice, 2 times sum over 1 to m f of n exponential will allow us to calculate the f of HKL values. So, what is very interesting here? What is very interesting here is the fact that if we have a C centered lattice, the presence of the C centered lattice will give us what we call as systematic absences, and those systematic absences occur when h plus k is equal to 2n plus 1. So, let us take a few examples and see how this happens. So, suppose I am now trying to measure in a C centered lattice, let us say I want to get a value of f of HKL, that means I measure the intensity of HKL. What I measure are the intensities of HKL. So, I have the diffraction experiment done, some spot appeared, so I index the spot. So, indexing again is a very crucial factor. So, I index the spot, and once I index the spot, I will identify the HKL values. If I know already that C centering is present, if I do not know anything about the presence of the C, let us look at it that way. I have a data, and this particular data tells me that suppose I look at this reflection statement which you have made here, f of HKL is systematically absent for reflections with values of h plus k odd, by taking some examples. Suppose I give you 1 4 0. So, this 140 will be H plus K is 5. So, that means it belongs to this category. So, whatever be the structure which crystallizes in a C-centered lattice, please note the words, whatever be the system which crystallizes in a C-centered lattice, whether it is monoclinic, orthorhombic, and what other is possible in a C-centered lattice. Monoclinic, orthorhombic, tetragonal does not have a C-centered lattice, so also hexagonal and cubic. Cubic can have a C-centered lattice, but then it becomes a F-centered lattice by symmetry. So, it is only in case of monoclinic and orthorhombic systems we can have this kind of systems. So, you see that you can cross check the ABC alpha beta gamma which you have got in some sense. So, 140 will be absent. Okay. Now, if we look at the reflection like 2 5 0, that will also be absent. Okay. So, if you look at something like 2 4 0, it will be present. Now, reflection like 1 3 0 will also be present. Now, why I am taking 0? It is not necessary to take 0. So, I can take for example 1 3 1. What will happen to this reflection 1 3 1? That 1 3 1 will have to worry only about H plus K even. So, therefore, for all HKL values, whether it is L can have any value including 0, this H plus K odd will be absent, and that therefore characterizes a C-centered lattice. So, now you see the importance of how diffraction can be used to identify the symmetry that is associated with the diffracting crystal. So, the system into which the diffracting material goes into now clearly says that this has to belong to a C-centered lattice, and depending upon the other the distances and angles, it could be either monoclinic or orthorhombic. Of course, the other symmetry elements which come are not associated with the centering, they are associated with the A and B and C directions depending upon the nomenclatures we have for different crystal systems. So, that part we will discuss later. What happens with respect to those 3 components which describe only the symmetry associated with directions. Those 3 or sometimes 2, sometimes 3, sometimes the same thing repeating 3 times. Those symmetry elements, if they also have translational component, those symmetry elements will also show systematic absences. But please note that those systematic absences will not affect all of HKL. It will affect only either projection reflections or axial reflections. This is a statement I am making, do not worry too much about it, we will discuss it in full detail as we go along. So, right now what we have discussed is a C-centered lattice.